So here we're going to be talking about exponents. Exponents and polynomials, essentially. So we left off about here. Part C was sketch the graph of x to the -1. So what is this function? X to the -1. This is 1 over x, essentially. So we can do that table of values. X and f of x equals x to the -1. And we can like list some values, like so -2, let's say, -1, -0.5. Let's say 5, -5. And you see, okay, so when we calculate this, 1 over -2, we know that that's going to be basically -0.5, which is going to be -0.5. -1, well, that would be 1 over -1. So that's just going to be -1. When x is a -0.5, that's going to be 1 over -1/2. So that gets flipped. So this becomes -2. 1 over -5 is going to be just -0.2, I think. Yeah. And we can do some more values. So these are some negative values. You can choose your own. Some positive values. I'm just gonna do another table, some positive values. So let's choose maybe 1/2, 1, 2, and 5. Let's say. So 1/2, that would be 1 over 2. So this is just 2. 1 over 1, of course, is going to be 1. 1 over 2 is just 1/2, 0.5, and 1 over 5 is 0.2. You can think of this half here, like 1 over 1/2, 1 divided by 1/2, is like how many halves go into 1? Well, it goes in twice. So you can kind of do that. And this function, 1 over x, is a very important function. You're going to see it like repeat over and over again. So let's just try to sketch it. So plot the points. You notice that 0, is that 0 defined? No, right? Because you can't divide 1 divided by 0. So there's no value there. And just plot the other points. So at 1, we get 1, etc. I'll try my best. This is f of x is equal to x, the exponent -1. So basically, that's the function. And it does repeat in other courses. I've seen this function. It's a classical function. So this is 1 over x. Now, what do you notice? It's kind of special, actually. If x goes to 0, or as x gets larger and larger from in this direction, what happens? Right, like so as x goes to infinity from this direction, it goes to 0. If x goes to negative infinity this way, what happens? X goes to 0. What happens when x goes to approaches 0 from the right, like you're traveling this way? What happens? It goes to infinity, right? What happens when x approaches 0 from the left? Negative infinity. So you actually learn this in calculus, limits and when a function approaches. So it's about observing this. Okay, good. So note that all properties that hold for positive integer exponents also hold for negative integer exponents. Before we were just talking about the positive exponent cases. So what I'm saying is they also hold for these negative integers as well. This is basically a summary, sum of a summary. If x does not equal to 0 and m and n are any integers, then this. Here, this one is just essentially x to the power 1 over m times, let's say, m is equal to 1 over n, and the other is m. We can write it this way. Which we'll talk about when we talk about powers and roots. So roots, so far we define exponentials basically only for integer powers, but we also want to give a meaning to expressions like 4 over to the power 1 over 3, or 7 to the power negative 2 over 3. Or let's say something like this, x to the power 1 over 4, or let's say x to the power 2 over 3, something like these. So we want to understand roots essentially. We learned before in the previous slide, that was the summary, that x to the power m to the power n is equal to x to the power m times n. So this is very important. So we can consider this x to the, and we know that x is basically the same as x to the power of 1. They're equivalent. So let me write something down. So x to the power x to the power 1, they're equivalent. So this is the same as saying x to the power 1 over m times m, which is the same as saying x to the power 1 over m times m. And we know this because, let's write a little note. Because 1 equals 1 over m times n. So this will imply x is therefore equal to x to the power 1 over m times m. I just changed the n's to m's here. So essentially, it makes a lot of sense to define this x to the power 1 over n as a number which, when raised to the nth power, gives x. Let's just circle that. So this implies essentially, so x to the power 1 over m is a number which raised, which one? Raised to the nth power gives x. So an example here, 5 to the exponent 1/7 is that number which when raised to the 7th power gives 5. So it is that number, so 5 to the exponent 1/7, let's rewrite it. When it's raised to the power 7th, gives, what is the answer to this? 5, yeah, perfect. I'm just making sure you're like kind of listening. Good. So this next one, -1 to 125. So it's -125 raised to the power 1/3. So when it's raised to the 3rd power, the answer would be, therefore, yeah, -125. So, so this part, when it's raised to the 3rd power. So what about this, -125? I think someone said it correctly, 5. I didn't ask that part, I asked when it's raised to the power 5. So which is the number? So this is asking which number raised to the power is -125. So for example, x to the power 3 is equal to -125. So what number raised to the power 3 gives -125? So this implies x is, right, perfect. X is equal to -5. Hope this makes sense. And then our last example here, this is 10,000 raised to 1/4. It's a number which when raised to the 4th power gives 10,000. So let's try to solve that. So x to the power 4 is equal to 10,000. So this implies, therefore, x would be, anyone? 10, right, 10. So you see 10,000 to 1/4 is 10. Good. So what is the number? -9 raised to 1/2. So we want -9 raised to the 1/2. This equal to x. So this means where essentially x squared is equal to -9. So is this possible? No, right? You can't, well, it is possible in complex numbers, but we're not going in that course in complex numbers. In real numbers, no, is the correct answer. So there's no solution. Because -9 to 1/2 is not a meaningful as a real number. again, it's gonna, and there's this area called complex numbers, but we don't deal with them in this course, unfortunately. Did you guys talk about complex numbers in high school? Anyone? No? No hands up. Okay. All right. So we can now properly define the nth root operation. So the nth root, if n is a positive integer and x is a real number, then x to the power 1 over n is defined to be the real number satisfying this particular equation, which makes sense. So what's the next part? So it's defined by this. And it's subject to like these following conditions that we kind of know, but they're a little tricky. So if x, let's do the second one. If x is greater than 0 and n is an even integer, then x to the power 1 over n is a positive number satisfying this equation. If x is less than 0, which we just found out using that example of the -9, and n is an even integer, then x to the power 1 over n is undefined for our purposes. And this was the example of -9 to a half was undefined. Because of course, -9 is less than 0. And here, of course, n is equal to 2. An example of the second one would be, let's say 16, like that's positive, to the exponent 1 over 2 is equal to, well, is this equal to 4 or -4? We have 16 is greater than 0, and we have n is equal to 2. So which one is it? 4 or -4? Because it can be the square root of +4 or -4. So it's the positive one, so not this one. Okay, so the number x to the power 1 over n is called the nth root of x, and it is denoted by n and then the square root x. If n is equal to 2, we simply write the square root of 2. So an exponent, or an example here, so x to the power 1 over 3, we can write it this particular way, like the 3 comes out front, then the square root symbol, then x. So they're the same thing, tomato, tomato. Another example would be, let's say x to the power 1 over 7. That's the same as 7 root x. There's a 7 there. And x to the power 1 over 2, these are all examples, is equal to the square root of 2, or sorry, x. What did I write that? X. I'll just make this a bit more clear. So we don't actually write the 2 here. I could write a 2. Let's use a different color. I could write this 2 here, but we don't actually need to. So don't write the 2. So to put this another way in words, let's say we have x to the power 1/3. To say this in words, if you like words, this would be the third root of x. So how to say it properly. So for roots, we have the following rules that make our lives essentially easier, which is this. Yeah. So let's evaluate this using that rule. So our n here is 3. I'll give you a second to do this too. X equals 32. Y equals 2. Now, you can do this along with me. So we have, I'm just copying the question down. To evaluate these individually would be difficult, right? Like I would need a calculator. So if we apply the rule, how do we do this? Pardon? Yeah, exactly. Because like evaluating this individually and then multiplying this, it's a little too difficult. We want to make our lives easy, right? So life can be hard sometimes. So we apply the rule. So 32 times 2 is 64. And then we can evaluate this. So what number to the power 3? Yes?
4.
4. Perfect. 4. That's it. So this is the number. 4 is the number raised to the third power, gives us 64. So it's just applying that rule. Now, so that was easy-ish, but sometimes life can be hard. So an example of this, don't make this common mistake. So what I'm saying is, don't make this mistake. Oh, we do have a quiz today. Person leaving. Anyways, so don't make this mistake. These are not equal. They're not equivalent. And why is this? So here's an example. Let's say n is equal to 2, x equals 4, and y, let's say, equals 9. So we would see that we can take the square root of 4 and the square root of 9, and we would get 5. But if we take like the square root of 4 plus 9, that's equal to the square root of 13, which isn't 5. Here's another one for you to evaluate, and you can work on this. So you start with, it's sort of like bedmiss. You start inside the brackets and work out. It's the same idea in computer science and everywhere else. You start like inside and then work out. So let's write this out. You can do this too at the same time as I do it. So inside, what do we get here? 5. So then this is equal to square root of 11 plus 5, which is then square root of 16, which is equal to 4. If this helps you, I'll write a little side note. 3, I'll just write this out this way, is equal to x. So x to the power 3 equals 125, therefore x must equal 5. Yes?
Let's say you have instead of square root 4, let's say you have square root 5 up in the example.
Where? Square root here? 4?
Yeah, let's say that was 5.
Okay.
4.
Okay.
How would we like evaluate that, or would we not?
If you're not allowed to use a calculator on your test, then you wouldn't be able to, right?
Okay. Okay.
If you can use a calculator, then I would probably just use a calculator. Or you just if this was a 5, then it would be like, okay, well, yeah, you can't say it's like 4, right? Because you don't know it, right?
Yeah.
So you would have to just kind of say, okay, 9 plus 5 is the square root of 14. This is 3. This is, you could try to estimate it a little bit in your head and say, okay, no, not really. Like, because this is going to be, yeah, I'll probably try to be careful in terms of the numbers I give you. Yeah. Sometimes the question, should I allow you to do give you a calculator or not? Because then I could give you more difficult questions. But previously they said no calculator. So I'm just trying to follow the rules. Personally, I would use a calculator at that point. So rational exponents. So far, we have been giving a meaning to expressions of the form x to the power k, a comma, where k is any integer. So basically, k can be positive, negative, etc. Or even it can be 0. And also where k is equals to 1 over n for some n. So for example, x to the power k can be equal to x to the power 1 over n and n root x. So next we want to understand like this form of x to the power n over n. They're like, it's to the exponent, sorry, like it's difficult to see, but. So if n and m, they're like fractions, and n and m are integers, and m is greater than 0, we can define it in this way. So basically, x to the power m over m, we can bring out by the rules. We can bring out the 1 over n. I'm applying the properties here. And this is an exponent, so we can apply it this way. So we get like this particular formula. So this definition excludes the case, essentially where x is less than 0, even when m is even. So why? I'll just make a little note down here. So an even root of a negative number is not meaningful. As a real number, as real, of course, as we know. So for example, if x is less than 0, and let's say x is equal to -5 and m is equal to 2, again, we have that case of here m is even. For example, x to the power 1/2 is equal to square root of -5. Not very meaningful, so it excludes this particular case. Also, if, like, for example, m is equal to 4, 4 root -5, not very meaningful. Oh, back here, what I was just trying to say is just don't add them like in this way. Like, be careful. Don't see this and then think you can separate them out and things like that. That's the main purpose of it. Pardon?
You do it separately first and then add the whole number?
It depends on the question. Like, if you're over here, don't suddenly combine them. Or if you're in this situation, don't suddenly separate them. Sometimes people just go from this situation and they think they can separate them out, and don't do that. Like, understand the operations on both of the numbers. Like, first you add them, then you take that square root. Don't think you take the square root of each number individually. That's the main purpose. So let's evaluate these. We can try to do them while I write them out. So I'm just, it's all squared too, so I'm just rewriting it in this manner, then evaluating the number inside the brackets first. So x, let's say, to the power 3 equals 27. So what number is that? 3, yep, perfect, 3. Because 3 times 3 times 3 is 27. So you can kind of check in your head, like, what number gives us 27? So go try kind of different numbers, but 3 times 3 is 9, and then 9 3 times, well, 9 twice is 18, and then one more time is 27. So this is 3 to the exponent 2, which is equal to 9. What about this y? So this is y to the power 3 to exponent 8/3. We can rewrite it. Bring in the 3, or the 1/3. Write it this way. To exponent 8. So what is inside the bracket? Yes?
Who was it?
I don't know. I thought, yes?
For question A, in that example, we not just reduce this to just be the square root of 27?
Square root? What do you mean?
Like, you have 3, the cube root.
Yeah.
And then we have afterwards, the exponent. Do we not just reduce it?
Yeah, that's what I'm doing. I'm reducing it to 9.
Skip the 3 to the power 2, just.
How would you do that, though?
With the multiplication of the 2, would you not just cancel it out and then make the square root of 27?
Do you get the same answer?
You get the same.
Did you? I'm asking you. I'm trying to just get you to answer your own questions. Because, yeah, like, you have to kind of like try things, like a trial and error in math a lot of the time. So like you just try it and you see like, can I answer my own question? And then, oh, this didn't work. And then why didn't this work, right? Like, and just try. Yes? Yeah.
Okay. So y to the 3 is on B.
Yep.
Y to the 3, and now it's cube group, they cancel each other out.
Yeah.
And it just becomes y to the 8.
Right, perfect. Good. That's the answer. Yeah. So the next one. So I'll write a little note down here. So x to the power 4, let's say, is 625. So what would that imply about x? So x would therefore be, you might need a calculator for, yes? 5. Yep, perfect. And so now we can write this out. So 5 to the exponent -3. So that's going to be 1 over 5 to the power 3. That reciprocals we learned before. And this is 1 over 125. So we're going to, so this is a summary of basically the properties of exponents we've learned so far. I suppose P and Q are rational numbers and X and Y are positive numbers. We have all of these properties, of course. I'll just put them in a box here. And this is the summary. So you notice, of course, that most of these identities, most of these identities, they've been what we've been like learning essentially. So they are not new. The one you have to kind of watch out for, I'll highlight it, is number 3. So this is basically if X and Y are basically not positive. Then most of these properties still hold. 3 is the touchy one. The most of these. Properties still will work. So just be careful. Just with basically the star one, the one in purple. So an example of why 3 is not always our friend is something like this. So if we have, like, let's say, let's go back to blue. So let's say we have -3 exponent 2 to exponent 1/2. Well, is it this? Is it like -3 to exponent 2 1/2? So then this is like -3 to the 1, which is -3. Or is it this one? -3 exponent squared equals 9, obviously. And then you take that square root, which is 3. So it's this way. So these are not equal. So this is why that third property here doesn't sometimes hold. So you have to just be careful of this negative when there's negatives in the numbers. But usually if, let's write in a different color. X to the power, like let's say P and Q is usually X to P times Q if X is positive. This will hold all the time. Now, so we have an actual question that's like more challenging here to do. So let's do this question together. And we can let's, for the purposes, assume, make that assumption that X and Y are positive. Okay, so let's start doing this question and see if we get the right answer. So if we could distribute the -4 in the bottom, and there's different ways to do it. So my steps might not be your steps. You might do the top steps first. I might do the denominator. It doesn't matter as long as we get the right answer. So I'm going to leave the top for now. You don't have to. I'm just distributing the -4 in. Now I'm going to distribute the half in the top. I'm just doing it like step by step. Oops. Okay, and now we use that property and we multiply them through. So 4 times a half. This is a classical question too, so you really should know it or learn it if you don't like. Notice I'm leaving the half here for last. Now 4 times a half is 2. -8 times a half is a -4. This is x to the power -4, y to the exponent -4 is a half. So we could group the like terms. And just, there's a lot of extra steps that you don't have to do. So 2 subtract -4. This is sometimes people fall for this one. Times y to the exponent -4 subtract -4 half. Do like these exponents. So this is x to the power 6 -4, subtract -4, that's going to be y to the power 0. We know what that is equal to. That would be x to the power 6 times 1. So x to the power 6 times this half is equal to x to the power 3. So that is our final answer. Let's put it. Did you guys get that? Yes?
Now that we just, when we see y to the -4 over y to the -4, we just cross those out and then just move on.
Yeah, you could.
Okay.
Yep, that's perfectly fine too. Like I said, like there's more than one way to do this. Right. This is just like step by step, for example, if someone doesn't know anything, that kind of thing. But yeah, and if you were to cross it out, I would just go like dot, 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 like something like that. Just so you remember that you're crossing it out. I'll just give you a second to write this down if you haven't. Has everyone? I also always post this too. But I see like these types of questions, like they're important questions. Okay, one more topic. Polynomials. So earlier we studied quadratic functions. So polynomials occur in so many applications. The defining property of a quadratic function was the highest power of the variable, essentially was 2. We don't need to limit ourselves to powers of 2. We can define functions that have as large powers as we want. So one nice family is these things called polynomials. So a polynomial is basically, this is the format of a polynomial. So it's equal to the coefficient a0 plus, this is a1 times x plus a2 times x squared plus etc. an times x to the power n, where n is a non-negative integer. Let me rewrite this this way. So a0 plus a1x plus etc. a2 times x to the power 2. And you see the pattern, I hope. An to the x to the power n. So this n is essentially called the degree. So this is called the degree of the polynomial. Let's just call it poly. And these a's are basically called the coefficients. So they are called the coefficients. The x's are the variables. So examples of polynomials, and then we'll see in seminars. So this is an example. Where a0 is equal to 7, a1 is equal to -3, this 3 is equal to 4, a4 is equal to 6, and etc. And a7 is equal to -8.5. What is the degree? So n equals 7, so this is the degree of the polynomial. So that is 7. Another example would be like P, this polynomial, x to the power 3 minus 0.2 to the x to the power 11. Kind of confusing, but you see the coefficient here in front of this x to the power 3 is 1. And this coefficient is -0.2. So n here is 11. And the degree of this polynomial is 11. So the simplest case actually is, let's say the polynomial, well, not the simplest, but x to the power 2, n is equal to 2, and a2 is equal to 1. So can you think of a function that is not a polynomial? So examples of this would be not polynomials, the sine function, not a polynomial. X to the power -2 is not a polynomial. Those powers have to be positive. And x to the power, let's say 5/2 is not a polynomial either. Okay.